711. This one is more complicated than you would expect just from looking at it. Seems like it'd be obvious that you could just, oh, well, if the measure of every set is 0, then if you start with a set, you can just, like, take a point in your set and take out a neighborhood of that, and by scaling that neighborhood, like, smaller and larger, well, smaller if necessary, then you can reduce the size. You can find a subset with size like between alpha and like alpha minus epsilon for some epsilon. Like there's some epsilon such that for every number between alpha minus epsilon and epsilon, you can find a set with that measure. And you should be able to do this until you would get down to 0. But there's no good rigorous way to do this unless you think to use Zorn's lemma. And that's really the heart of this proof, is that you have to use Zorn's lemma. So, what do we need for Zorn's lemma? We need a partially ordered set. So here's our set. We're going to let this be script A is the set of all intersections A intersect U, where U is open, and the measure of A intersect U is less than or equal to alpha. Obviously, A is non-empty, and why is that? That's because, I don't know, you just... Oh, no, A is not empty. A is clearly not empty because the measure of A is strictly greater than 0, so it can't be empty. And how about script A? And given any A and A is Borel and null, i.e. as measure 0. So it has an open neighborhood of measure less than or equal to A. There's probably a better way to say that, or phrasing, but whatever. But the point is that script A is not the empty set. That's pretty important here, because otherwise this would be really boring. So we want to apply Zorn's lemma. So we need to make a partial order. So let script A be partially ordered by inclusion. And we want to use Zorn's lemma. So what does Zorn's lemma say? That if for every... here, I'll just write it out. To apply Zorn's lemma, we must confirm that every, I'm going to call it a no, because that's wrong. Every totally ordered subset of A has an upper bound. Because Zorn's lemma says that if every totally ordered subset has an upper bound, then the set itself has a maximal element. So let script B be a totally ordered subset. Totally ordered subset of script A. So we have to show that script B has an upper bound. So for each, my notation gets a little strange here, and I wonder if it's a little bit superfluous, but oh well, we'll get by with it. For each script B and B, we will denote by u sub b the open set such that b is equal to a intersect u sub b, because that's what elements of script b look like. That's because that's what elements of script a look like. Okay. So should I define? Yeah, let's define this now. Let u be the union over all b in script b of ub. So then no, we don't want to do this quite yet. See, this is where this notation is a little confusing, because we have the b's, but we're also working with the ub's, and sometimes we want to work with the b's, and sometimes we want to work with the u's. Anyways, so then the union over all b in script b of the b's themselves. Well, what is this? This is just the union over this script b of a intersect u sub b, and this is just a intersected with the union over all b and b u sub b. So now let's let u be the union over all b in script b script b's of ub. I claim that a intersect u, let's make that a little curvy, not too curvy. Sure. This is contained in script A. Is that what we want? Yeah, it is what we want. Alright. U is open because it's a union of open sets. So A intersect U is Borel, and it's finite since it's a subset of A. So by proposition 7.5, go back to that, mu is inner regular on A intersect U. Well, what was proposition 7.5? Proposition while I'm scrolling, I'll explain. Proposition 7.5 told us that Redon measures are irregular on all sigma finite subsets, so not just the open ones. So because A is finite, it's in particular sigma finite. That's like a lot more finite than sigma finite, because it is finite. So it's, anyways, A intersect U is a sigma finite Borel set, and so Redon measure is an irregular on it. And so that makes it easier to work with, because now we can let K be contained in A intersect U be compact. Then U is an open cover of K. So what can we do? So there exists B1 through Bn in script B such that UB1 through UBn cover K. However, since script B is totally ordered, there exists just one B in script B such that K is contained in UB. And so here is why See, everything that we've done in this proof so far, we had a lot of stuff to work with because we had a Redon measure. We had irregularity with compact sets. We had so you might have thought like, oh, well, in this defining of the script A that we defined before, why did we use open sets? Why didn't we use something different? We used open sets precisely because it allows us to use this type of argument. We needed to have open sets so that taking these unions would give us something open. We needed to use we needed this to be a totally ordered set, and we needed to be able to use an irregularity because if we just had a countable collection here, we wouldn't be able to find this single element B here like we did here. Compactness is really powerful, and it's really nice when you're able to use it. And we really needed to have an irregularity in order to use it and stuff. So anyways, this is just a really nice argument. Everything just sort of fits together, and everything does, like nothing could be replaced by something different, except maybe some of the notation could be improved. But the essential things that we're working with can't really be changed. They all play important roles. So what do we have now? So K, well, K is contained in U sub B. So what else do we do? We chose K to be in A intersect U. So then K is in A intersect UB. And so mu of K, certainly it's going to be less than or equal to the mu of A intersect UB, but this is an element of script A, and so this is less than or equal to alpha. So by inner regularity then, and now this is really nice because we have irregularity on A intersect U. Even though this isn't necessarily open, this could be Borel sets, even though like they're nice because they're generated by topologies, they can be really strange. But we have irregularity on even these really strange sets. And so we can take the supremum, the mu k's, such that K contained in A intersect U, K compact. But then by the argument we just gave, we know that each of these for any compact K contained in A intersect U, the mu of it is less than or equal to alpha. So this particular, so the supremum is going to be less than or equal to alpha. And so, hence, A intersected with U belongs to script A. So, let's see here, now what? By construction, for all B in script B, A intersect UB is contained in A intersect U, because A intersect U is just, well, U is just the union of all the UBs. So, hence, so thus, A intersect U is an upper bound for script B. All right. Scrolling up. I'll leave this here in case there are some issues with loading, because my computer is doing that thing where it goes really loud and catches on fire almost, and so this might be a little might take a while for things to load on the screen. Hopefully I should be able to have money to buy a nicer, better computer one of these years, but we'll see what happens. So this confirms that every totally ordered subset. I guess I'm being a little wordy here, but maybe we're just like basking in the proof that we just gave and how kind of nicely it worked out. So, hence, by Zorn's lemma, script A has some maximal element E. And let me see, did I need to define, yeah, so, and we're going to write this as A intersect UE, where UE is an open set, and there we go. I now claim, so why do we do all this? Because I claim that this is exactly what we want. So, let's see here, for all A in script A, mu A is less than or equal to A. So certainly, mu of E is less than or equal to alpha. Now, so I guess this isn't quite as nice. We have to do a contradiction proof, but it's not too bad. We don't stay in this contradiction land for long. Because it's kind of like when you do a proof by contradiction, you're assuming something that's not true, and so you enter a world of mathematics where all the statements that you prove are generally not true or questionably true, and you get a lot of weird results. And so when you go into contradiction land, you don't want to stay there long because it can sort of mess things up, and it's a weird place to be. So that's one of the reasons why I think people don't like contradiction proofs, is that they don't tell you about the actual mathematical world. They tell you about contradiction world where things don't make sense and where all statements are true. Assume for contradiction that this holds. Then mu of E is less than mu of A, so let A be in A but not in E. Since, well, I wrote that, okay, the singleton set A is it's bounded in null. No, it's Borel. I wrote bounded, I meant Borel. But we don't need to write it at all because we could just talk about it because it's so obvious. We just talked about the fact that singletons are sets. Why are singleton points sets? Singleton points are sets because this is, let's see here, x is, we have mu as a Redon measure on x. I'm pretty sure that this space is Hausdorff. Let me scroll back up for a second. Look at the problem statement. Mu is a Redon measure on x, such that mu x equals 0. Well, yeah, okay, mu of x equals 0 for all x and x. So obviously every point is measurable, because otherwise the problem statement doesn't even make sense. That does bug me though. Does having a Redon measure mean that our space is like Hausdorff or like nice in any way? I don't think necessarily. But in this problem, we know that there's no issue here because singleton sets are measurable because they have measure 0. So then there is an open neighborhood. Why did it disappear? Open neighborhood U of A whose measure is less than or equal to the difference between alpha and mu E. But U union UE is open, and what is the measure of this thing? U union UE. Actually, let's not include that and there. Well, this is certainly going to be less than measure of UA intersect U. That is... No, oh, okay. I continued on the next line with plus mu A intersected with... Why did I write E sub U? I meant to write U sub E. Man, what was I doing earlier? Was I drunk when I made this? So, yeah. So, this alone is not true, but when you add that plus in, it certainly is, because this union certainly, like, when you take the union together, you might overlap in the middle and lose some stuff, so this inequality holds. But then what do we know about this? We know this first part is less than or equal to alpha minus mu of E, and the second part, well, just by definition, is precisely the measure of E. So we get this. So it's equal to alpha. And what else? A intersect U union UE contains A intersect U. So what does this tell us? So the set E, I'm going to write it like this, is squiggly less than or equal to A intersect U union UE. And let's just put a not. Oh, this is horrible notation. Oh, and now it's all gone. U is... So here, when you typically write a contain but not equal to, typically kind of looks like that. So if we want to do this, it would be like here. Do you know what? No, let's just do this to mean like instead of doing like where you have the contain subset of but not equal to like this. Here, what we're going to do is we're going to do what we do with inequalities. With inequalities, we don't say less than or equal to but not equal to. What we write is we write just less than, and so this means E squiggle less than A intersect here in script A, i.e. E is less than or equal to this set with respect to the partial order that we have defined on script A. But this contradicts the fact that E is a maximal element of script A. So I guess it's not so bad that we had to do a proof by contradiction, because this is kind of the typical thing that you do in a Zorn's lemma argument. It's you say, hey, here's a maximal element, and this does what you want it to, because if it didn't, then you could find a larger element. That's typically how these Zorn's lemma arguments tend to go, I think, sometimes. At least once that I can recall. I think that's how the proof of Han-Banach goes. Nah, but whatever. So hence, UE equals alpha. This completes the proof. That's because this confirms that given any alpha between 0 and the measure of A, we can find a set E that has precisely that measure. And that is what we wanted to prove. And now we are done.